Welcome to our Quantum Deep Dive.
Today, we're diving into the story of a true architect of the quantum revolution, the physicist Juan Ignacio Cirac.
You know, his ideas weren't just abstract theories. They were the very first practical blueprints for building a quantum computer. And this entire deep dive is based on a fantastic, comprehensive essay by Jörg Oa Schneppe.
All right, so here's how we're going to break this down today. We'll start with the big dream of a quantum computer and meet the young pioneer himself, Ignacio Cirac. Then, we'll get into the weeds of his revolutionary ion trap blueprint, see how that theory shockingly became reality, explore his much wider legacy, and finally, take a look at what's next on the quantum frontier.
You know, to really grasp how huge Cirac's breakthrough was, we got to go back in time to the late 20th century. Quantum physics was this incredibly beautiful field of ideas, but when it came to actually building something with it, well, physicists were hitting a brick wall. The theories were amazing, but the path forward was totally dark.
And this was the massive question just hanging over everyone's head. I mean, this wasn't about making slightly faster computer chips. No way. This was about creating a completely new kind of machine, one that could actually tap into the bizarre, mind-bending, and powerful rules of quantum mechanics itself. And this is the challenge that a young physicist from Spain was about to tackle head-on.
And that young physicist was Juan Ignacio Cirac. He was born in Manresa, Spain, back in 1965. He was just this incredibly gifted student with a massive curiosity about how the universe really works, which of course led him to study theoretical physics in Madrid.
But here's what really sets Cirac apart. He had this amazing ability to see a connection between two worlds that most people saw as totally separate. On one side, you have the deep, weird reality of quantum mechanics, and on the other, you have the cold, hard math of information theory. You know, how we store and process data. He was one of the very first people to really ask the question, what if you could encode information inside the quantum world itself?
And that difference is just everything. A normal computer bit is basically a light switch, right? It's either on or off, a 1 or a 0. That's it. But a quantum bit, or a qubit, that's more like a spinning coin. Right before it lands, it's not heads or tails. It's in this weird state of being both at the exact same time.
Exactly. That whole spinning coin thing is what we call superposition, and that is the absolute magic ingredient. It's what allows a single qubit to hold so much more information than a boring old classical bit. So if you could link a bunch of them together, you could, in theory, run just a mind-boggling number of calculations all at once. The potential was insane, but there was a huge problem.
And this is where the story really takes a sharp turn. After his studies, Cirac goes to the University of Innsbruck to work with his mentor, the amazing theorist Peter Zoller. And it was there, working together, that they came up with an idea that was just completely revolutionary.
Right, because they were going after the one problem that was stopping everyone. Qubits are so delicate. I mean, the tiniest little disturbance from the outside world, a stray bit of heat, a tiny vibration, can make that spinning coin fall over and totally wreck the quantum information. That's a process called decoherence. And for years, it made building a quantum computer seem like a total fantasy.
So their solution, which they published in 1995, was so elegant and, this is the important part, it was actually doable. Okay, so step 1, you trap a line of charged atoms, ions, in an electromagnetic field to hold them perfectly still. Step 2, you use super precise lasers like tiny little fingers to poke and prod the quantum state of each ion, turning them into qubits you can actually control. And step 3, this was the real stroke of genius. You use the ions' shared wiggles, their vibrations, as a quantum bus to pass information between them and link them together in this bizarre state called entanglement.
And you really have to get this. This was not just another theory paper. This was a recipe. It was a step-by-step architectural plan for building a real working universal quantum computer. It basically told all the experimental physicists around the world, hey, that impossible dream, it's not impossible anymore. The race was officially on.
And the impact was just immediate. I mean, that 1995 paper didn't just get a little bit of attention. It was like a bomb going off in the physics community. It kicked off this huge global competition between labs, all scrambling to be the first to turn this beautiful theory into a real physical thing.
And one of the key players in that race was a guy named David Weiland over at the National Institute of Standards and Technology, NIST, here in the US. Now, Weiland was an absolute master of trapping and controlling ions. So this partnership between Cirac's brilliant theory and Weiland's incredible lab skills, it became the textbook example of how science is supposed to work.
And the progress was just ridiculously fast. Okay, get this. In the exact same year the paper was published, Wineland's team successfully demonstrated the very first 2-qubit quantum logic gate, which is a fundamental building block for any computer. And it was based directly on the Cirac-Zoller model. I mean, theory became reality in just a few months. And from there you can see the biggest awards in science just started rolling in, recognizing that this was the moment. Quantum computing went from science fiction to a real engineering problem.
But here's the thing, Cirac's impact didn't just stop with the ion trap, not even close. That work became the foundation, and he became this central figure, basically helping to build the entire global quantum community from the ground up.
Yeah, in 2001, he took on this huge leadership role at the world-famous Max Planck Institute in Germany. And under his direction, the theory division there became this global magnet for the smartest people in quantum science. He was shaping the research agenda not just for Germany, but really for all of Europe.
His genius just wasn't a one-off thing, it was foundational. I mean, his work branched out everywhere. He developed theories for quantum repeaters, which are absolutely essential if you ever want to build a quantum internet. He was a pioneer in quantum simulation, which could completely change how we design new medicines. He even developed these powerful mathematical tools called tensor networks, and became a key advisor, helping to launch these massive European research projects and shaping policy for a whole generation of scientists.
And all of that brings us to today. The blueprint that Cirac helped draw up is now being built on by thousands of researchers all over the planet. But the quantum revolution is far from finished. Actually, the toughest parts of the quest are still ahead of us.
And we're still fighting the same two big monsters. You've got decoherence, that constant buzzing of noise from the environment that just wants to kill your quantum information. It's a relentless enemy. And then you've got scale. I mean, going from a handful of qubits to the millions you'd need for the really world-changing stuff, that is an unbelievable engineering mountain to climb.
So, to fight those enemies, we need a really powerful weapon, quantum error correction. And guess what? That's another field where Cirac has made huge contributions. The core idea is so incredibly clever. You basically take the information from one perfect qubit and you smear it across lots of messy, imperfect physical qubits. This gives you backup copies, so you can find and fix errors without ever actually looking at and destroying the quantum information itself. It is absolutely essential if we're ever going to build reliable machines.
And the reason everyone is working so hard on this stuff is because the potential payoff is just world-changing. Quantum computers could break the encryption that protects our entire digital world, but they can also help us create new, perfectly secure ways to communicate. They could simulate molecules to design life-saving drugs or create brand new materials we can't even dream of today. And they could solve these insanely complex problems in finance and logistics that are just impossible for even the biggest supercomputers we have.
So this leaves us with one last big question. Thanks to pioneers like Ignacio Cirac, we have the architectural plans for this completely new technological age. The technology is coming, one way or the other, but the choice is about how we actually use it, for good, for bad, for solving our biggest problems, well, those choices are going to be up to us. In the end, Juan Ignacio Cirac didn't physically build a quantum computer. He did something that was arguably way more important. He showed the world that it could be built. He was the one who drew the map that led all of us out of the theoretical wilderness and straight into the age of quantum engineering.
And this deep dive was only possible because of the incredible and insightful work of Jörg Ove Schnepphat. If you want to read his full, detailed essay and find out more, we absolutely recommend you visit schnepphat.de. Thank you for joining our Quantum Deep Dive. Goodbye.
Schnepphat.de is a private project by Jörg Ove Schnepphat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.